Welcome back, everyone. Hopefully by now you watched the first video on apparent weight problems and blocks on an inclined plane. You've taken the Learning Catalytics quiz on Canvas. That's just participation. You have unlimited attempts, and you get a little bit of better feel for things. This video is going to be about a specific type of problem called an Atwoods machine. There are several ways to look at Atwoods machines and how to derive your equations. I will focus on one, although there's a way that I like to do as well that I might mention at the end of the video too. An Atwoods machine is this setup right here. What we have is a pulley at the top and then a mass hanging from either side. These masses could be equal or maybe one is heavier than the other. But depending on the setup, you'll see what it is. At this moment, I have 100 grams on both of them. And so they are an object at rest and they stay at rest, right? No matter where I set this configuration, it's not going to suddenly start falling down. It's not going to suddenly start moving up. It's going to stay there whenever I let it go. And apparently the testing of the emergency phone went on during this video. Oh, well, that scared me. We also know an object in motion stays in motion. So if I set this pulley into motion, it's going to keep moving up, right? Same thing here, set it in motion this way. And if it doesn't collide with itself, it should just continue to move. Got to make it not hit something first, right? But when it's at rest, it stays there. If I put one weight that's a little bit heavier than the other, so I take an extra 5 grams. So these are about 105 each. If I added an extra 5 to one, it shouldn't surprise you that now that one is a little bit heavier than the other, there is now a net force that's not 0. And so when I let this one go, it accelerates. One falls down as the other falls up, right? So how do we find the acceleration in this type of problem? An Atwoods machine problem is one that I would definitely encourage you to make sure you know how to solve and how to do. Not only is there a learning catalytics module on it, there's a couple practice problems on it, there's some quest problems on it. It would be surprising to me if there's not an Atwoods machine problem on the exam. You never know. I haven't seen the test yet, but I would expect to find an Atwoods machine problem. And if you know how to do them, they're really not too bad at all. So let's take a look at maybe finding the acceleration in an Atwoods machine problem. So here we have our setup. We have 2 masses. We will call them mass 1 and mass 2. And they could have any value. It doesn't really matter what their numbers are. And I'm sure if you had a quest question that these numbers would be given to you. But for now, we'll just call them mass 1 and mass 2. And we have a pulley. Let's say mass 1 is the heavier one. And mass 2 is the lighter weight one. Which means when we let this go, mass 1 will move down and the lighter one will move up. You need to pick a positive direction for the Atwoods machine problems, which is a little tricky because if we just say up is positive and down is negative, these pulleys change those directions. So if up is positive and down is negative, then these masses that would indicate they're moving in different directions, which in a way they are. But in actuality, you hopefully can see that because of the pulleys, overall, that's the same direction. And so what I usually pick is whichever way it moves, I'm going to call that the positive direction. So the heavier one is here. And even if you wanted to maybe flip it over, oh, hey, I turned around and looked at it the other side. Now it's moving to the right. So it doesn't really matter which side we have is which. Just pick a positive direction. And I'm going to call counterclockwise the positive direction for this setup. And so I'll show you 2 different ways to look at this problem, and whichever way makes more sense to you is what I would encourage you to do. And if you look at one and you feel like that's more confusing, ignore it and just focus on one. So here's our first way. And our first way is to look at each of these masses separately and combine equations for them together from there. So I'm going to first just look at mass 1. So if I just isolate M1, what's happening to M1? Well, there is a tension that is up on M1, and M1 has a weight that is pulling it down. We'll call it M1G. That's it. There are only two forces. So I don't feel like I need a chart to figure this out. I can use my net force equation, which is just F equals ma. So to sum our forces, we do positives minus negatives, or we subtract the positive forces from the negative forces. And then we set that equal to M times A. So remember, I am calling down on the left one, my heavier one down, we're going to call the positive direction. So what is my net force? It's going to be M1G minus tension, so minus T, equals M1A. I'm only looking at M1, and I get this equation. This is going to be my first equation here. And that's it. Now let's look at M2. M2, very similar. We have an upward tension and a downward weight of M2G. And so we set up our equations. But remember, on this side, we called up the positive direction. Positive was in this direction. So for the equation, it's going to be a little bit different. And we're going to say it is T minus M2G equals, so that's our net force. Remember, our equation is net force equals M times A. That's our big equation that we're focusing on. So here's our net force equals MA. And again, we're just looking at M2 here. So I can say M2A. So here's equation 2. So now I have two equations. T minus M2G equals M2A, and M1G minus T equals M1A. From here, we need to combine these two equations algebraically. Again, there is several ways to do that. You could just add the two expressions together. That is probably the simplest way. But I will solve it slightly different. We'll do it this way. I'm just going to solve for T on equation 2. Tension equals M2A plus M2G. And again, this is not the only way to solve this problem algebraically. And now we have an equation for tension. So let's rewrite equation 1. M1G minus, and instead of T, what am I going to write? My expression over here. M2A plus M2G equals M1A. So to recap, we looked at each mass individually, and we set up equations. We have M1G minus tension, so down minus up, positive minus our upward force, equals M1 times A. And then the opposite, T minus M2G equals M2A, because these are traveling in that direction. We took those two equations and combined them. And so now we'll do a little bit of algebra, because the tensions in all the ropes are the same. M1G minus M2A minus M2G, the negative distributes out, right? Equals M1A. I'm going to add M2A to the other side. I'm solving for acceleration here, is usually what we're trying to find in these problems. And I get M1G minus M2G. So the weights, the difference in their weights equals M1A plus M2A. We can simplify this a little bit more. M1 minus M2 times G equals M1 plus M2 times A. And then finally, we get M1 minus M2G. So the numerator here is their difference in their weights divided by the total mass equals acceleration. And so that's one way to solve it. I'll zoom out here so you can get a look at the whole thing. And maybe if you wanted to take a picture of the work, that would be fine, or pause the video. So again, to recap this method, we set up two equations. We used equation 1, this downward positive force minus the upward negative force. So M1G minus T equaled M times A, F equals MA. For equation 2, it was moving up. So we did T with the positive direction minus the downward direction, M2G equals M2A, because I'm just looking at M2. So we got these two equations, equation 1 and equation 2, which we rearranged equation 2 and combined into here. And then from there, it's just algebra until we end up with isolating A, and we get this expression here. I like to think of this problem a lot of times in a slightly different way. So I will show you a secondary method to consider this problem. There's a few others, but these are what I would say the main two. If this makes perfect sense to you and you follow the math and it makes sense and you want to do it this way, great. Do it. Don't worry about the second way. But if you're still a little confused, I think the second way is a little bit more conceptually driven rather than formula driven. So here we have our setup. M1, M2, as such. And we can only really consider this problem, and I'll be specific here, mostly because it'll show up in later units. If our pulley is this ideal, perfect, frictionless, massless pulley that has no effect on the problem at all. So if we assume we have an ideal pulley that has no effect on the problem at all, and this string here is this frictionless, massless string, we can shortcut this setup a little bit. And realistically, for most of our problems, it doesn't really matter all that much. We could actually do the experiment, and the string and the pulley, if they're low enough friction, aren't going to make much of an effect. But I will be specific if we're not considering the string or the pulley at all in these problems. And because of that, and because I know the tension is going to pull up in both of these directions, right? Tension is pulling up on mass 1 and it's pulling up on mass 2, right? Instead of thinking it like this, I just like to picture this string getting smaller and smaller and smaller and smaller. And I kind of redraw this problem almost like this. We have M1 being pulled to the left because of its weight of M1, right? Or maybe I'll write it as M1G, pulling it to the left. And then there's a tiny little string here, but the string is going to cancel it out. And M2 here, and M2 is being pulled to the right by what? M2G. The weight of M2 pulls this down, and the weight of M1 pulls this down. And if we picture this string just getting smaller and smaller and smaller and smaller until it's really teeny tiny, like a micrometer wide, the tension here in this string really doesn't matter. We might as well think of these masses as connected. And one mass is being pulled to the left by what? The weight of M1G. And one mass is pulling to the right by what? The weight of M2. And so now let's just treat it as an F equals MA question. F net equals M times A. So what's our net force? Right? Well, it's one force minus the other. And whichever one we want to call the bigger force, I'm going to call the positive force. I think in the previous one, I said the M1 was the bigger, and we can keep that the case. So we'll call this the positive direction and call this the negative direction. And so what's our net force? These two subtracted from each other, right? M1G minus M2G. That's our net force here. The tensions are going to cancel out. So what's causing the net force? The difference in their weights. Equals M times A. And here's where this one gets a little bit trickier. We're considering not the masses individually like we did before. We're considering it as a whole big thing. And so what's our mass? The total mass of everything that's being accelerated. So M1 plus M2 times A. And there we go. We've got our equation. So I find this one to be a lot more conceptually driven. You have to make a few assumptions, but the formula ends up the same as the one before. And if we wanted to solve for A, we get this right here, M1G minus M2G divided by M1 plus M2 equals A. And this equation right here is really just a net force divided by the mass of the problem equals A, right? Where our net force, what's causing it to accelerate? Their difference in weights. What's the mass? The total mass of the system equals the acceleration. And so either way you want to think about it is awesome and great. I would definitely expect an Atwoods machine problem that might be solved similarly to this one. Would not be surprising at all if it showed up on a test. So hopefully that helps with the Atwood machine problems. From now, if you want to, you can now go on into the Canvas lecture college course, and you should also find another learning catalytics quiz there entitled Atwoods Machine. We pretty much just answered all the questions that are on that module, but I would encourage you to go in and maybe check your understanding. I think that one only has about 3 questions. It's very short. And again, you have unlimited attempts on those, so do them until you get 100. Hopefully this helps a little bit. I'm sorry I wasn't there today, but that's how things happen sometimes. So I had to be at tennis. You can rewatch this video and the other one as many times as you want. So hopefully the videos can be a helpful tool for y'all as you're looking at finishing up Quest 4 and beyond. If you have remaining time in class today, after you've watched the videos, you've done those learning catalytics quizzes, don't forget that the post lab is due tonight and that your quest will be due next week. I probably will not see you on Thursday unless you're in 7th period because of the PSAT. But next week on Tuesday, we will just pretty much have that time to review maybe and answer some of the questions that might have come up from today's videos that you might have, and really look at the quests. Remember, the exam 2 will cover both quest 3 and 4. So projectile motion as well as forces and these force problems. Hope you all have a great day. Feel free to reach out to me through email or Remind if you have any questions, and I'll see you all next time.